applications. His research focuses on nanomaterials, electrocatalysts, carbon dioxide reduction, and energy-related technologies such as supercapacitors and solar cells. He continues to actively contribute to research, mentoring, and international collaboration in advanced materials and science. Please join me warmly welcoming Dr. Hemraj Yadav for his plenary session. I request Dr. S.S. Desai, Associate Professor, Department of Management Studies, Rajaram Bapu Institute of Technology, to felicitate Dr. Professor Yadav. I, I also request ma'am to share a token of appreciation from RGCS Consultancy. Over to you, sir.
Yeah. Good morning, all. It is my pleasure to be here in this IC Smart 2026 international conference organized by RIT. And today I will talk about whatever research we did on nanomaterials, and we prepared several nanomaterials and we tested different applications of these materials. So I will talk about, I think this is not working. Yeah, I will talk about Shivaji University and some basic of nanoscience, then climate change, then circular economy, little bit about IPR, and various applications of these nanomaterials. So I work in Shivaji University as an Ramanujan fellow, and Shivaji University, we know that, which was established in 1962, and we have more than 283 affiliated colleges, more than 36 departments and school on campus, and our campus is biodiverse. So I will not go into detail about this. So I work at School of Nanoscience and Biotechnology, and here we offered 4 programs, that is BSc Nanoscience and Technology, MSc Nanoscience and Technology, as well as BSc and MSc Integrated Nanoscience and Technology, and PhD in Nanoscience and Technology. Because we know that the nanoscience has various career opportunities in various fields. So you can see here the glimpses of instrument and facilities which are available in my school. So we have several instruments for synthesizing and characterizing these nanomaterials, and some sophisticated instruments. Our students are placed all over the globe. They are pursuing PhD, postdoc, and research job at various countries. So we know that the nanoscience, that is, we are studying the properties of material at nano level, and whose dimensions is between 1 to 100 nanometer. And we are using these materials for various applications. So you can see here the history of this nanoscience, and we know that we are using these nanomaterials since our ancient time, and we know that in 2001 Indian government, they initiated nano mission, and they supported various research activities under this nano mission. So On the scale, you can see the nano means very dwarf, or Greek word that is dwarf, or meaning very small, or whose dimension is 10 raised to minus 9 meter. So in this nanotechnology, we study the properties of these materials. We know that atom, molecules, and we combine these and we make small materials. And you can see here the nano on this scale. We can see here the size of sand, that is in micrometer, right? And the size of atom, that is zero point 0.1 nanometer. So like this, you can consider the how nano is small. So we are in the playing with these properties of materials at the nano level. You can see the atomic scale, bulk scale, and nanoscale. These are different. And we are studying the properties of these materials at nanoscale. And you can see here, these materials are classified into different dimensions, that is 0 dimension, 1 dimension, 2 dimensional, or 3 dimensional materials. And we can get different structures of these materials. And we use these materials for various applications. And we know that the discovery of graphene in 2010 from the graphite, just putting tape on that graphite and just pulling out, we can get graphene, and which is nothing but the nanomaterial. And Professor Richard Feynman, on his talk, he talked about this. There are the plenty of the rooms at the bottom, means nano have a lot of scope. And this is a small science with a huge potential. So we know that the nanotechnology is science where we play with electronics, material science, chemistry, physics all together. This is interdisciplinary field, and we develop materials with various structures, and we apply these materials for various applications. So we prepare nanorods, nanosheets, and we apply for various applications like industry, biomaterial, energy, IT, and various other applications, consumer goods. We are using sunscreens, that is nothing but the nanomaterials. And these materials have some environmental concerns also. We need to study that one also. So you can see how these materials are prepared. Basically, we need to prepare these materials by using two approaches. One is top-down approach and another is bottom-up approach. We can make small by cutting large materials, or we can build atom by atom or molecule by molecule. We can grow clusters and make nanomaterials. So these two classes of these materials. Apart from this, you can see here in detail, we can prepare these materials by using chemical or physical methods. There are several methods. We go for physical deposition, vapor deposition, like that. And chemical, several solgel, hydrothermal, we are using that methods to get these nanomaterials. Or we can go for methods, biological methods. From bacteria, we can also get these kind of materials, or plants, like different nanomaterials. So you can see here what happens at the nanoscale. The properties of the bulk material and the properties of the nanomaterials are different. And if you go to the nano level, the optical properties, mechanical properties, electrical properties, these properties are changing compared to the bulk material. So if any bulk material is, if it is inert, it can become catalytically active at nano level. If it is opaque, it can become transparent. So these kind of properties are changing. And why these properties are changing? Because of the surface area to volume ratio, or the quantum mechanical model, or quantum confinement effect, or the surface plasmon resonance effect. So these factors affect the properties of these materials compared with the bulk material. So you can see the how size matters here. If I take a cube and if I make small pieces of that cube, you can see here we can get larger surface area. So this is the way we can improve the surface area, and that surface area is available for reactions, and we can get maximum surface area of that material compared to the bulk material. So this is the example how we can make any material small and we can get larger surface area, and with that surface area we can get higher catalytic properties. So this is example. So this is not new science. We are using this since our ancient time. We know that we are using Ayurvedic churnas, powders to treat our disease, and we know that we are using some Hirak Bhasma, Nag Bhasma or Suvarna Bhasma, that is nothing but the gold nanoparticles, mercury nanoparticles which are used to treat the disease. We are coating these materials on various uh, equipments like swords and other materials, so improving their mechanical properties. If we coat the carbon nanomaterials or mix these materials, they can improve its mechanical properties. So these materials are used since ancient, and we know that the gold nanoparticle and how the color of bulk gold is different. So depending on the size of that material, we can also get different optical and chemical properties of this material. So we are basically mimicking the nature. We know that the lotus effect, right? The water droplet loving and hating nature of this lotus leaf because of its microstructure. So similarly, we can develop nanomaterials which can act as super hydrophilic, super hydrophobic in nature based on these structures. So we can get this kind of properties. So apart from this basic, now question is, how do you know the climate change is real? Yesterday, during inauguration, Honorable Jayant Patil Sahib mentioned that this is the land where we face a lot of flood areas and we are facing climate changes, right? We are facing the global climate change. So how do you know the climate change is real, right? So the answer is that the rise in global CO2 level, that is currently more than 423 ppm, rise in global temperature and the melting of ice, these are the signs which shows that the climate change is real. And what caused the climate change? Like we are dumping lot of CO2, right, into the nature, and this causes increasing temperature, and because of that, the global temperature is also rising. Even if you waste the food, that one is also causing lot of CO2 into the nature. So eat wisely, right? Don't waste the food. So we know that the climate change, there are different sectors and we need to reduce this climate change, or we need to reduce the emission of the CO2 as the global CO2 level is rising. And we evidenced this climate change with the floods or droughts and wildfires and extreme heat conditions. All these are the signs that shows that the climate change is real. So apart from this, what we have to do? We have to restrict the cutting of the trees. We are losing the resilience on the forest. So we need to restore our forest. That is the most important. And if you see that the capacity of absorbing CO2 by the plants is also decreased drastically. And we need to restore the plants, forest to maintain our geological balance. So we know that the plants, how they convert the CO2, and we learned this in the class 10th or 4th standard. So we know that there are major global issues regarding these worlds. Today we are facing several challenges, that is health, energy, uh, water and food. And we need to address these challenges. And we are facing global issues. And I would like to quote here Barack Obama's quote, that is, we are the first generation, we are facing the impact of this climate change, and the last generation that can do something for this climate change. So we know that we are dumping a lot of carbon dioxide, carbon monoxide into the atmosphere, and also the farmers from our regions or farmers from Punjab, Haryana, they are burning lot of stubbles. We are in the region of where we grow lot of sugar canes, right? After cutting that sugar cane, we are burning lot of stubble, and this is causing rise in CO2 level. So we should not burn that stubble. We can convert that stubble into fertilizer. So that is the problem. And we know that the major energy source, that is the sun and the earth core, and we know that we are using several renewable energy sources, we are dependent on the fossil fuels, and we know that currently we are facing the several issues. This is uh, global war between Iran and US Israel. So we are depending on these fossil fuels, and these sources are depleting day by day. And we know that the sun doesn't shine sometimes, the wind doesn't blow sometimes, so we need alternative energy sources. So what we can do for that? We can develop several materials which can act as alternative sources for these global issues. And for this, we can make our earth or environment better or sustainable. We can develop several processes which are sustainable, which do not harm the environment, which are eco-friendly. So for this, we know that we are using several electronics day-to-day life and consumer electronics, and these all electronics, they contains several elements, and if you see, the demand of these elements is rising day by day, and the availability of supply of these elements is decreasing day by day. So you can see here so many critical minerals we are consuming in several electronics and other applications, and the supply is in critical state. So you can see here the product lifespan, how these product lifespan. So we are using products, we are after using, we are throwing or we are dumping that products into the environment, and this is the example, that is linear economy. So instead of linear economy, we have to move to the circular economy, where we can make, we can use, and we can again recycle. So that is the most important case. Rather than linear economy, we have to go to shift to the circular economy, where we can use products, we can recycle the product. So that is most important. And some of the companies, they are doing these practices in their products. Some of the industries, they are recycling the clothes, their consumer electronics products, they can be repaired and recycled. So this is the policy for circular economy we have to follow, because we know that the Mahatma Gandhi said that the world has enough for everyone's need, but not for everyone's greed, right? So we have to recycle, we have to follow circular economy. And apart from that, the next part is, that is IPR. IPR is very important. Not only patent, design also, then trademark or GI tags, these are very important. And Government of India, they launched the IPR awareness mission. And because why IPR is important? We know that the battle of the patent for the turmeric and its medicinal use. The US claimed the turmeric copyright patent, that is the origin of this battle. And when Dr. Mashalkar came to know that US filed patent in 1995, and they claimed that is turmeric have medicinal properties, and they want their copyrights for that turmeric. But when Dr. Mashalkar came to know that, he has gone through several literature, our ancient literature, Granthas and Rigvedas, and he challenged that patent in 1997, and he won that battle, and we got the right for this turmeric and its medicinal use. So intellectual property is very important. And similarly, we know that the case happened recently with Prada. Prada, that is international brand, who copied the design, that is our local Kolhapuri chappal. So this is the importance of property rights, intellectual property rights or product property rights, designs. So you should aware that these properties are very important. So we know that the Kolhapuri chappal is very famous, and it has got GI indications in 2014, and Kolhapuri jaggery, which is has received a GI indication in 2019. So innovation is very important, and for innovation, emerging technologies, then interdisciplinary collaboration or funding, infrastructure, these are very important and policies matters a lot. So recently we are in the era of AI and several smart materials, and we need to foster this research innovation. We need to identify these several problems, we need to collaborate, and we can solve the several problems. So role of IPR is very important here. So patent, copyright, trademark, these are very important. So there are several challenges while we go for patent, designs and copyright filing. We need to understand a lot of ethicals. So three P's are very important here. So that is patent, publish and prosper. So if you have any idea, if you have any novelty, you should go first for patent, then go for publication, and if it is industrially useful, then you will become prosper, right? So three P's are very important. And we know that the problem of publish or perish, we are publishing a lot of papers. That is also important to increase our ranking of universities and everything. But apart from that, we need to solve the real world challenges. So this is the current scenario for Indian patent publications. More than 1 lakh patent granted this year by Indian Patent Authority. So there is a global shift, right? So there is a global shift for patent, startups and innovations. And recently, government of China, they introduced a new PhD rule for research scholars. If you want to get PhD degree, you have to go to the next level, not only paper-based level. You have to go to the product-based level. So this is the new rule for Chinese PhD students. So paper, not only paper, they need to go for the product. So these kind of policies the nations are developing. So we are doing several kind of collaborations, and with the help of our collaborators from all over the globe, we are doing research in the field of material science. And I work with Professor Jung Sik Kim at University of Seoul, and we developed several materials for self-cleaning and photocatalytic applications. Also, we developed FET-based sensors. Then I worked with Dongguk University as an assistant professor, where we developed several materials for photoelectrochemical applications. We developed solar cells and other materials, supercapacitor. So we developed basically nanomaterials, and we tested their applications for photocatalysis, bactericidal, biomedical applications, sensors. We also developed sensors. We developed supercapacitors, energy storage applications, photovoltaics, that is solar cells. We developed a catalyst for hydrogen and oxygen evolution, and we are also developing materials for these CO2 reduction reactions. So we are dealing with these nanomaterials, and we know that the photocatalysis, and we are mimicking this photocatalysis process for semiconducting materials. If you shine the light on the semiconducting material, it can generate electrons and holes, and we can utilize that electrons and holes for to drive the chemical reactions. So this is photochemistry. So we developed several nanomaterials, like we know that the titanium dioxide, that is ubiquitous component of the universe, and which has been used in consumers, pigment and various applications. So we modified this TiO2 because TiO2 is semiconductor material which is having energy band gap 3.2 electron volt, and it is UV active material. We are using this TiO2 zinc oxide in sunscreens, which blocks the UV light. It absorbs UV light with its wide band gap energy. So we modified this TiO2, we doped with metal, we made it composite, and we made it visible light active. And by using that material, we degraded various dyes in the visible light. So it acts as a photocatalysis and degradation purposes. Also, we developed several self-cleaning materials, and we transferred that technology to the Auto Industry Company Limited, Korea. And these materials were used in the automobile sectors for windshields and headlight lamps. they are coated with these kind of materials and making them super hydrophobic or super hydrophilic, whatever, anti-fogging materials. And these materials are nothing but the nanomaterials. So also we developed some composite materials of these TiO2 and graphene oxides, and we use that materials for benzene gas. We know that the benzene is carcinogenic gas, and we can degrade that benzene gas with the help of these materials under visible light. So this is the regarding applications of this material for degradation of dyes and gases. So you can see here the example how we experimental setup, how we degraded that benzene gas under visible light. Also we developed these materials, we doped these materials with several dopant, and we tested its antibacterial applications under visible light, because we know that we need sterile surfaces in hospitals and public sectors. So we can coat these kind of materials, make sterile surfaces, or we can inhibit or control the growth of bacteria. So we modified these materials with nickel, iron, copper, and we tested its applications for antibacterial applications. With the help of our collaborator, we tested its applications for also biomedical applications. Particularly, we know that the cancer cells, as we know that the titanium dioxide is semiconducting material and which is UV active, so we can bind the drug molecules to these materials and we can deliver the drugs to the particular site with the help of the UV light. So we prepared these nanocoral structures of titanium and we bound that material with anti-cancer drugs, and these materials we tested for drug delivery purposes for cancer cells, and this can be used as a targeted drug delivery application purpose. So you can see here the drug bound doxorubicin with this TiO2 nanoparticle, and it can be released with the help of the UV light, and we studied its biomedical applications. Then similarly we developed another material, that is, we know that the silica nanostructures. So here we use that silica nanostructures for the drug delivery applications, and which is controlled with the help of pH. TiO2 we control drug delivery with the help of light. Here for silica we control its drug delivery application with the help of pH. So we have used these nanomaterials because these are having very high surface area. We can bound drug molecules and we can deliver that drug molecules to the particular cancer cell site. Similarly, we have developed several nanomaterials and we tested its applications for antibacterial purposes, chitosan TiO2 composite, then magnetic nanoparticles for hyperthermia applications, and some MRI imaging applications. So these nanomaterials are used in various biomedical purposes. Also several nanomaterials for uh, hydroxyapatite kind of materials we use for to study its biocidal activity and cytotoxicity. As Professor Wyatt mentioned regarding sensors, he has developed a sensor, right? So similarly, we were developed sensor for glucose sensing, which is based on the nanomaterials. This is a simple technique. We just deposited copper nanoparticles on simple glass, and which is we used here non-conducting glass, and we made it conducting by depositing these copper nanoparticles, and we use this glass as an electrode for sensing glucose in the analyte with the help of electrochemistry. So here we can use these nanomaterials as a sensor also. Apart from that, we used these nanomaterials for supercapacitor applications, and we know that we store energy and we need energy again. So we use supercapacitor batteries, and they both have different energy density, power density, their storage mechanism is different, and so we used these materials and we studied different parameters of the supercapacitor. Yeah. So we developed several composite of these metal oxides nanostructures and we tested its supercapacitor applications. We developed binder free electrodes using this graphene nanoplatelet, and we also developed binder free electrodes and we tested its supercapacitor applications. Also we used cellulose nanoparticles and metal organic frameworks and its composite for supercapacitors and energy storage applications. We optimized their compositions, and we tested its applications. The next topic, that is energy conversion, that is solar energy. We know that photovoltaics, and we convert this light into electrical energy, and we developed this kind of materials for indoor light purposes also, and we developed these materials for indoor light as well as outdoor light. We developed several nanomaterials, which and in 2023, Professor Lee, he is the president of Korean Electrochemical Society. He also visited Shivaji University and he coined the concept of artificial light cells. So we have developed this kind of cells. We can put these cells in below the LED panel and which can again generate electricity. So that is the artificial light cell. So we have developed this kind of nanostructure materials which can generate electricity and we can again store energy. Apart from that, already Professor Wyatley told regarding this electrochemical water splitting. We are also working in this field and we are generating hydrogen, oxygen, and we are conducting some CO2 reduction reactions. So one of my PhD students, she is working at Biotechnology University, and Professor Jayant Gunchkar, he is supervisor, main supervisor, I am the co-supervisor, and she has developed some 2D nanomaterials and we tested its applications for oxygen evolution reactions. So these 2D layered double hydroxides we modified with different dopants and we tested its applications for oxygen evolution reactions. So these kind of nanosheets are very efficient for these oxygen evolution reactions, and at minimum potential around 200 millivolt we can get oxygen evolution reactions. So she have developed these kind of materials. We made composite of that materials and we tested its applications for OER. So these composites, nano sheets of that material, composites are efficient. Then another, my PhD student, she is working on gas sensors and she is using these LDH materials for gas sensing applications at room temperature, particularly an O2 gas sensor. And we developed this kind of sensors based on these LDH nano sheets. Then another student, he is also working in this LDH and he developed the electrocatalyst materials for OER applications and HER applications. So we have prepared this kind of nano sheets, and these nano sheets are useful in different catalytic applications. Another student, she is working in the development of supercapacitors and electrocatalytic applications. She is developing some metal oxide based composites for supercapacitor and HER OER applications. And we are currently working on the CO2 reductions, and that work is undergoing on. We are using CO2 to convert into valuable chemicals, and we know that we can convert the CO2 into CO and other chemicals. We can get valuable chemicals. We know that the CO2 level is rising. I already mentioned in the introduction, and we can convert this CO2 and we can get valuable chemicals. And for this, there are different methods like chemical method, photochemical method, biological method, thermoelectrical method, and they have different pros and cons, but we are focusing on the electrochemical, and that research is going on. So with this, we need to solve several global challenges, and we need international or interdisciplinary collaboration. So with the help of that, we can do that kind of research and we can solve the global challenges. So we have one joint research project with Professor Wyatley and Professor Delikar. He is main PI for this project, and one more professor from Dr. Ilyas. He is from University Technology Malaysia. So we have got research fundings from Asian India collaborative R&D scheme from DST. So I visited there, they visited here, we are working on this, and this is project of development of some electrolytic materials for the several applications. We are working on that. This is the recent visit photo, and with this I would like to acknowledge the SCRB now become ANRF, then Asian India, Science and Technology, Shivaji University, Dongwik University, DY Patil University, and NRF, other institutes for their financial support. And our research thrives because of our students. So these are students working under our guidance. And in 2024, we celebrated Europe 100 years of Indian National Chemical Society. And we also do several science popularization activity for school students with the help of INEAS and DY Patil University. They have their social responsibility center, and this is for particularly for students to motivate the students. I traveled more than 8 countries, and all my trips are sponsored by the government. And I came from the rural background, and I reached at this level. So you can do it. So dream big, dream can transform to your thoughts, and it will result into action. So like our Dr. APJ Abdul Kalam said. So failure is just temporary, and success is autocratic. So Professor G.D. Yadav always said like that. So you should dream high and fly high. So Ano Bhadra Kartuvayantu Vishwata means this is Sanskrit sloka. Let the noble thoughts come to us in all directions, right? And Swami Vivekananda said, all observations go through into the 3 stages. First they ridicule, second they oppose, and third they accept, right? First they will laugh, they will oppose you, and they will accept you. So this is the, then one announcement that is yesterday I have received an invitation, and we have launched the special issues on architecting carbon neutral breakthroughs in oxygen evolution reaction, hydrogen evolution reactions, and CO2 reduction reactions. This is a special issue is now online, and you can submit your manuscript to the MDPI for this special issue, which is having impact factor around 4, and I am the serving as the guest editor for this special issue. And I would like to thank you, the organizers from RIT, directors, and all my friends for giving me this opportunity to interact with you. So with this, thank you.
Thank you so much, Dr. Yadav, for taking us through the journey of nanomaterial, circular economy, and IPR and its importance. Now we will take the questions.
Yes.
Thank you very much for the detailed talk about especially the application of the nanometals, and good to see nice high impact journal
Yeah.
papers. I do have a question about the modeling and simulation. I've seen all the experimental, synthetic, and everything. Have you gone through the modeling simulation part also, or do you have some collaborators with you?
Presently, till now, I haven't did anything modeling, but definitely one of my friend, he is doing that kind of things, and we last year we assigned that project to our master students, and that project is also already completed. So maybe we will submit that results to the journal, and we started in that way also. Thank you. Yeah.
Molecular dynamics is very interesting in this direction.
Yeah. Yeah. Thank you.
It's a very nice session from
Yeah. Thank you.
simple basics to
Yeah.
experiment level. My question is regarding supercapacitor. So how this nanomaterial will revolutionize the supercapacitor as energy storage? So some detailed insights or brief insights.
Yeah, actually, due to lack of time, I skipped that part because uh, which factors affects the charge storage mechanism. So we need surface area is most important, because this supercapacitor, that is surface phenomena, and that charges are stored on the surface. So we need high surface area materials. We know that the whatever commercial devices we are using, that we use materials like graphene, activated carbon. So these materials are having very high surface area. Some mob-based materials, metal organic frameworks, derived carbon, which is having very high surface area. So these kind of materials we are presently using as a supercapacitor. So basically we need to high surface area, but we need to also study its electrode and other electrolyte properties, its stability and other factors. Yeah, thank you.
Thank you so much, Dr. Yadav.
Thank you.